The Earth spins once on its axis every 24 hours at a speed of 1,000 miles per hour, giving us days and nights. The Moon, traveling 2,300 miles per hour, orbits the Earth once every 27 days. And together, over the course of 365 days, they speed around the spinning Sun, which is pumping out vast amounts of energy into space.
Big whoop. What's that do for me?
Hey curious minds, Dave here. Today's video is all about how 3 objects in space, held together by gravity, shape your experience as a human on Earth. From days to nights, seasons and moon phases, months and years, tides and eclipses. All choreographed by 3 celestial partners. This is a story of the Earth, Moon, and Sun, and how together with gravity, they rule your world. And we start with seasons.
Hey, are you guys ready for the pool yet? It's almost summertime. It's summer in the southern hemisphere? Crikey, it was way off.
Hey everybody, Dave here. Today's video is about why we have seasons here on Earth. So let's go ahead and get started by testing your seasons knowledge. Which of these 4 images most accurately shows the shape of the Earth's orbit as it goes around the Sun? And the answer is C. But please don't feel bad if you get this wrong. If you Google Earth's orbit around the Sun, most of what pops up is either misleading or incorrect. It turns out that the Earth's orbit is by far closest to a circle, but it's technically an ellipse. On average, we're 93 million miles from the Sun, but at our closest, we're 91 million miles, called perihelion for you science geeks, whom I love. And at times, we're 95 million miles from the Sun, called aphelion. Which brings me to my second question. At what time of the year is the Earth closest to the Sun? Is it the first week of A, January, B, April, C, July, or D, October? And the answer is January. Confused? Don't be. It's simple. The distance between the Earth and the Sun is not the cause of seasons. To hammer this fact home, if the distance was the cause of seasons, then the entire Earth would be experiencing summer at the same time, and the whole Earth would have winter at the same time. But we don't. While it's summer in the northern hemisphere, in the southern hemisphere it's winter. And now for the amazing science questions of the day. Number 1, which planet in our solar system has seasons most similar to Earth's? And number 2, which planet has the most extreme seasons? Stay tuned for the amazing answer. Now let's recreate what's happening to cause seasons here at home. I'm going to model what really causes seasons using a light meter app on my phone and a globe of the Earth in my backyard. And I'll take measurements of how much light energy is hitting the Earth all the way from the equator up to the North Pole. At the equator, the light is hitting my phone directly at a 90-degree angle. Imagine a tiny person standing on the equator. To them, the sun would be directly overhead. So that's where I'll begin. With my assistant Theo, I take a reading of light energy at the equator, then move up to the Tropic of Cancer at 23.5 degrees north latitude, up to Boise, Idaho at 45, the Arctic Circle, and finally the North Pole. Now let's take a look at the results. As we go further north, the amount of light energy goes down. At the equator, where the sun's at 90 degrees directly overhead, there's 800 lux of light energy. And at the North Pole, where the sun is on the horizon at 0 degrees, there's only 10 lux of light energy. Here's the thing though, that data was for an untilted Earth. In reality, the Earth is tilted 23.5 degrees off its vertical axis. Sometimes the northern hemisphere is tilted toward the sun, and sometimes it's tilted away from the sun. So I collected data for those scenarios as well so that we can compare our results. And here are the results. The red line on this graph represents how much light energy is hitting the Earth's surface at different latitudes when the Earth is tilted toward the sun. The blue line is when there's no tilt, and the yellow line is when the tilt is facing away from the sun. There's a huge difference. There's way more energy hitting the northern hemisphere when the Earth is tilted toward the sun, as shown on that red line. You can see that as the northern hemisphere is tilted toward the sun, sunlight is hitting the Earth at a 90-degree angle north of the equator, at the Tropic of Cancer. At the North Pole, it's hitting at a much lower angle, about 23.5 degrees, but it never goes onto the night side of Earth, giving it 24-hour-long days. We in North America also get much longer days, as we are on the day side of the Earth much longer. When the tilt of the Earth is leaning away from the sun in the northern hemisphere, sunlight is hitting the southern hemisphere at a 90-degree angle, and they are having much longer days. It's summertime in January. But the North Pole, it doesn't even reach the day side of Earth, and North America has a very low angle of light, and quite weak. And light striking a surface at 90 degrees and being so incredibly strong explains a lot of things you see in your daily life, like why you're so fast to sunburn on your shoulders and the tops of your ears, why people place solar panels facing the direction they do to generate electricity, why ski resorts are typically found on the north sides of mountains when the sun is in the south. So to summarize, seasons are not the result of the distance between the Earth and the sun. The tilt of the Earth results in the sun being higher in the summer and lower in the sky in the winter. It also changes the length of days for those time periods as well, which in combination give us our different seasons. So there you have it. The mystery of the seasons has been solved.
And the answer to the science questions of the day, first one anyway, is Mars. Mars has a tilt very similar to Earth's and therefore has seasons really similar to Earth's as well. In Mars' summer, you could almost even live there. And the answer to the most extreme seasons on Earth is Uranus. Uranus' tilt is at 90 degrees. It rolls along in its orbit as it goes around the sun. It's pretty crazy and extreme.
Next up, one of the most misunderstood topics I ever taught in class, moon phases. Imagine you're in a spaceship, looking down on the Earth as the moon orbits around it. As we look down on the top of the Earth and the moon during the moon's 1-month orbit, I noticed something. The moon's appearance never changes. The side facing the sun is always lit up. So if the moon's appearance from space never changes, why do we see it in different phases here on Earth?
A common explanation people give for moon phases is that it has something to do with the Earth's shadow. So let's go take a look at a model and see if that's even possible.
On the model, you can see the sunlight coming from this direction. And in all of these positions over the month, there's only one time the Earth's shadow could fall on the moon, here. But that usually doesn't happen because of the tilt of the moon's orbit, seen here exaggerated because of the constraints on my model. This is more realistic, where the shadows go over or under one another. You see, no shadow on the moon.
So why do we have moon phases? It's simple. Half of the moon is always illuminated by the sun. The phase that we see from here on Earth depends on how much of that lit up side we can see as the moon orbits around the Earth.
For example, when the moon is in this part of its orbit, we see the half of the moon facing the Earth, which in this case is the dark half, and we call this the new moon phase. At this position, the half facing us is mostly dark, but with a sliver of light on the left side. We call this a waning crescent phase. Here, the half facing us is dark on the left side and white on the right side. And remember, that's from the perspective of a person on Earth. This moon phase is called the first quarter.
Now, do we have to know moon phases for happy, successful lives? No, but I do think it's a good exercise in seeing things from a different perspective in order to understand what's going on. So now let's briefly check out how do we come up with these names for the moon phases. I have no idea where these moon phase names came from. This croissant is really good. But here are 4 words that you should know to describe the moon phases. Crescent means less than half full. In gibbous, well, that means more than half full. Waxing means getting bigger. I always think of Daniel and the Karate Kid, wax on. And waning means getting smaller. That's a great vocab word. You see it in literature all the time. And to remember if a moon is waxing or waning, there's a little rhyme. If it's wide on right, it's growing day and night. And then if the moon is half lit up, those are the quarter moons, first quarter and third quarter. And not because it's a quarter lit up, it's because it's a quarter and 3/4 of the way through its month-long cycle.
The moon phases are a very predictable cycle. Starting off at the new moon phase, where all you can see is the dark side of the moon, you start to see light on the right side, and you get to waxing crescent. It grows to the first quarter moon, and then to waxing gibbous, and then to the full moon. Then it goes the other way, where you start to get the waning gibbous, the third quarter moon waning crescent, and back to the beginning, the new moon.
What does any of this have to do with lunar eclipses?
Once a month, the sun, earth, and moon are all in a line, and we can see from the earth just the lit up side of the moon. We call this the full moon. When the earth, moon, and sun line up during a full moon, sometimes the moon's orbit is tilted so that the moon does go through the shadow of the earth. This we call a lunar eclipse. Now check out this time-lapse of a lunar eclipse. About 3 hours usually, but sped up into just a few seconds here. You see the Earth's shadow? 2,500 years ago, ancient Greeks wrote their suspicions that the Earth was a sphere based on this very site. And if you're wondering why the moon gets reddish during the eclipse, that's because some of the sun's light bends its way through the Earth's atmosphere and is kind of projected onto the moon in a sunset-y sort of way.
Lunar eclipses seem like they happen more commonly than total solar eclipses, but they both happen about 2 times a year. It's just that for a lunar eclipse, you only have to be on the night side of Earth to see. In solar eclipses, it's a different story. And there you have it. Moon phases, how they're named, and lunar eclipses.
Later on, we'll get back into moon phases and dive a little bit deeper into the moon and its mysteries. But for now, let's look at the most underrated result of the Earth-Moon-Sun system, tides. Remember in Despicable Me when Gru shrinks the moon and all the ocean waves just suddenly stop? If you didn't cringe when you saw that, you should probably watch this video. Hey curious minds, Dave here. Today we look at the difference between tides and waves and how Gru got it wrong. We learn the fascinating source of tides and look at how they've influenced life on Earth, in biology and in world history.
Seriously, Dave?
Tides are the rising and falling of sea level over hours, and waves are, well, waves. Tides are the result of the gravitational pull of the moon and the sun, while waves come almost entirely from wind, putting energy into the water as it blows. Which is why, if the moon were gone, we'd still have waves. And while waves are beautiful, tides have altered the course of history. So what on earth could be causing the oceans to rise and fall? Now imagine this hula hoop is Earth's oceans. My son here is the moon and my daughter is the sun.
Seriously, Dad? Do I have to wear this?
No, that's fine. You can take it off, buddy. Now the moon's gravity pulls on things, including water. So moon, pull gently on the oceans there. You see that? The ocean bulges out on the side facing the moon, and here's the weird part, it also bulges on the opposite side of the Earth. These bulges are where you find high tides on Earth, and in between, the low tides. And once every 24 hours, every part of the Earth moves through those bulges of ocean water. If you're on the coast when you're in a bulge, it's high tide, and when you're in between bulges, it's low tide. And since there are 2 bulges opposite each other, most places get 2 high tides and 2 low tides about every 24 hours. And now for a fun fact. While the moon pulls on Earth's oceans, it also pulls on the land itself and on you. Don't worry, you won't turn into a werewolf, most likely. Now the solid Earth moves just a few inches, only sensitive instruments notice, but the ocean water being sloshy moves a lot more. In some places just a foot or 2, but in others it's huge. Like in Canada's Bay of Fundy, the ocean can rise and fall 40 feet between high and low tide. I bet you people there pay attention to the tides. And now, it's time for the Seriously Dave question. Now, all planets and moons in our solar system are affected by tides to some degree, but which object is affected by tides the most to spectacular results? Stay tuned for the answer. And now it's time for my favorite part of this video, moon phases, tides, and World War II. Spring 1944, war rages in Europe. Allied forces would like to invade Europe from Great Britain, but they need to do it by sea, and they need some help from the universe. Specifically, a night with a full moon followed by a very low tide at sunrise the next day. Is this possible? Now we know that the moon affects tides, but what about the sun? Well, yes, the sun's gravity also pulls on Earth's oceans, though not nearly as strongly as the moon's. While the sun is huge, it's super far away. So let's take a quick look at the moon phases, because they're a result of the sun and moon's positions relative to Earth. It takes the moon around a month to orbit Earth, and its position around the Earth gives us our moon phases. All the while, its gravity and the sun's is pulling on the Earth's oceans. Sometimes the sun teams up with the moon, and other times they work against one another.
I hate you.
Now let's demonstrate. Now when the Earth, moon, and sun are lined up like this, we call this the new moon phase. And if those two team up and gently pull on that Earth, you can see it gets to be a pretty big oval. We call these spring tides, where the high tide is really high and the low tide is really low, and they happen at the full and new moon phase. These are my favorite tides because you can really explore tide pools and the incredible life that inhabits them. But what about during a first and third quarter moon phase? At these times, the moon's gravity is pulling perpendicular to the sun's. So sun, you pull up, moon pull to the side. I don't see much of a bulge on that one. Neap tides are, for lack of a better word, boring. The tides don't change much over the course of a day, which is great if you just want to hang out at the beach and not really do much of anything. And that brings us back to tides and their ability to alter world history. June 6th of 1944 was found to have the ideal conditions for Allied forces to free Europe. Soldiers could parachute into France and land during a full moon the night before the invasion. And then the ships landing via the English Channel with soldiers could travel under the cover of darkness the next morning and land on large open beaches at the low spring tide. These brave soldiers, with the help of the Earth, Moon, and Sun, successfully took back Europe, eventually bringing the continent peace and prosperity once again. But there's something that always bothers people. Why do both sides of the Earth bulge out? The answer is actually really fascinating once you understand it. It has to do with gravity and the fact that gravity gets weaker the farther away two things are from one another. This is no joke. The Earth's gravity affects you less on top of a mountain than it does at sea level, because you're further away from Earth's center of mass. It's not noticeable, but it is measurable. Now look at the Earth and Moon. The near side of the Earth is 8,000 miles closer to the Moon than the far side, so the Moon's gravity pulls more on the near side. It's still pulling on the far side too, but not as much. So even though both sides of the Earth are being pulled on by the Moon's gravity, the Earth and its oceans stretch. It's like my hands. Even though they're both moving the same direction, since one is moving faster, the distance between them increases. And this leaves the Earth with two high tide bulges to enjoy. And the answer to today's Seriously Dave question is Io, Jupiter's closest moon. They are so close that the gravitational forces of Jupiter cause Io to contract and expand, kind of like a paperclip being bent over and over again. As a result, its insides are molten and it is covered in volcanoes that are constantly erupting into space. It kind of looks like a giant jawbreaker to me. Thanks for taking this tidal journey with me. And if you made it this far, go ahead and like this video and subscribe to the channel. It makes a big difference for small creators like me. And next up, we have solar eclipses.
All right, I think I got it. I'm just gonna check it, see if it works. Oh man. Oh, it works. There are a lot of great videos out there about total solar eclipses, but this one is different. These are the things you think you know, but you probably don't about the Earth, Moon, and Sun. And when we're done, you'll see eclipses in a totally different light. Now, eclipses happen when the Moon casts a shadow on the Earth. Only this model is wrong. If the Earth is 6 inches in diameter, the Moon is actually 1.5 inches.
That's not all though. The Moon is 30 Earth diameters away. In real life, that's about 239,000 miles. In my backyard, with a 6-inch Earth, it's 15 feet. And one more problem with my at-home Earth, Moon, Sun model. At this scale, the Sun would be 55 feet tall and just over a mile away. Because the Moon is so small and so far away, its shadow can barely reach the Earth. And the final twist is that the Moon's orbit is actually tilted. It doesn't go straight around, but at a 5-degree angle. So that itty-bitty shadow usually goes over or under the Earth. And no shadow on the Earth means no eclipse.
Luckily for us, the Earth and the Moon perfectly align once every couple of years to give us total solar eclipses. But unfortunately, like most of life, it's still not that easy. And that's because of how small the shadow actually is. Typically 93 miles across, and coincidentally, the exact same size as the big island of Hawaii.
And you have to be in the shadow to see the total solar eclipse. Not the huge penumbral shadow here, but the tiny umbral shadow there. If you're in the penumbra, it's a partial solar eclipse. Interesting, but easy to miss. On top of that, the Earth is rotating at anywhere up to 1,000 miles per hour, with you on it. And the Earth is orbiting around the Sun at 67,000 miles per hour, and the Moon is orbiting us. So the shadows move across the surface on a curved path at 2,300 miles per hour, the same speed as an F-22 Raptor. Oh wait, actually it's 1,000 miles per hour faster than the F-22. It's sounding a little harder to get into that shadow, isn't it?
And finally, millions of years ago, the Moon was much closer to the Earth and much bigger in the sky. So big, it would have covered the entire Sun, making a larger shadow, making eclipses more common, and also more boring. And millions of years in the future, the Moon will be further away and smaller. The shadow won't reach the Earth, so there won't be any more total solar eclipses, just annular eclipses. Cool, but not as exciting. But now, right now, the moon and the sun appear the exact same size in the sky. Because while the sun is 400 times larger than the moon, it's also 400 times further away. And as a result, the moon perfectly covers the sun, but not its atmosphere.
And you heard that right, the sun has an atmosphere.
So the moon has to be in the right place, the earth has to be in the right place. The moon's shadow has to fall in the right place, you have to be in the right place. The sun has to be the right size, the moon has to be the right size. Their distances have to be exactly what they are now, not what they were, not what they will be. And then, only then, will you see the cosmos for what they are. Perfection. So now we've covered the big four: tides, eclipses, moon phases, and seasons. But don't go away. Coming up, we have the next level of moon phases and a video on whether or not it's worth it to stay up to watch a lunar eclipse. And don't forget to like and subscribe to the channel if you're learning anything today. Hey everybody, Dave here. Today we take a deeper dive into moon phases.
Remember, we see moon phases because half of the moon is always lit up. The moon phase just depends on how much of that lit up side we can see from our position on Earth.
But here's a quick question. How much of the moon can you actually see? And does the moon have a dark side? One that's always in shadow?
You have only ever seen one side of the moon with your very own eyes. In fact, the first time human eyes directly saw the far side of the moon was in 1968 on the Apollo 8 mission.
And that's because the moon is tidally locked with Earth.
It once rotated on its axis like this, but now, one side is permanently facing the Earth as it goes through the month. And that's because of the gravitational pull of both the moon and the Earth on one another.
And are you wondering what the far side looks like? No? Well, I'm going to show you anyway.
Drum roll, please.
But is the far side dark? Was Pink Floyd right?
Just look at the new moon phase. Is the far side facing the sun dark?
So there is no dark side to the moon, only a far side. I guess you do need an education, Pink Floyd.
And now for the real next level of the moon phases, the patterns.
The moon's phases are not random. Where you find the moon in the sky is not random. When it rises and sets, not random. So if you really understand them, you can use the moon phases like a clock or a calendar. Let's take a look.
The Earth has night and day because it rotates on its axis. And as you go from the night side to the day side, that's sunrise. And when you're facing the sun, that's noon, during standard time anyway. And then you get to sunset and midnight all in a 24-hour period. So can a person on the night side of Earth here see a new moon phase here? Nope, they're facing the wrong direction. I've shaded in everything you cannot see from the night side of Earth. So what time will they first be able to see the moon? Well, that's right, sunrise, when they rotate onto the half of the Earth facing the moon. And now I've shaded in everything you cannot see from the day side of the Earth. The new moon will then be highest in the sky at noon, and then people on the day side of Earth will lose sight of it at sunset.
Actually, you can't see a new moon. It's dark and right next to the brilliant sun. All right, so the next question. When will the third quarter moon phase be highest in the sky?
Pause the video if you don't want help, but here's the moon at its third quarter phase. I'm going to shade the far side of the Earth-Moon system, the side directly away from the third quarter moon. You first see it here at midnight, and it's at its highest at sunrise. Then it'll set at noon.
Want more questions? When does the waxing crescent moon rise and set?
Here's the waxing crescent moon phase position. I'm going to shade in the side of the Earth facing away from the waxing crescent moon, where nobody can see it. It's first visible when you rotate to the part of the Earth halfway between the sunrise and noon at 9 a.m. here. It gets highest in the sky at 3 p.m. here and sets at 9 p.m. there.
Now, how knowing all of this about moon phases can help save your life.
Imagine you're stranded on a tropical island and it's the middle of a waxing gibbous moon phase, which lasts a week. You somehow know that in 1 week's time a cruise liner will be passing by your island at 3 a.m. Too far away to see because of the curvature of the Earth. You have no clock, but you do have a flare. How will you know when to fire your last flare so that someone sees it from the ship? Let me know your answer in the comments.
Now you've heard there's a total lunar eclipse coming, but the big question is, should you watch it? Now here's everything you need to know to make that decision. Number 1, you should know that eclipses are really slow. I'm not going to call it boring, but watching tortoises race is more exciting. Number 2, You should know that they always happen at god-awful times where any decent human being should be in bed, sleeping, dreaming of flying. Number 3. You should know that the moon will get red when it enters into the Earth's shadow, the blood moon, which I think is a mediocre name. I'd call it a rose moon or a strawberry moon. You should also know that if you miss this lunar eclipse, another one will be visible from where you currently are sometime in the next 2.5 years, which is a lot different than total solar eclipses. If you want to see one from where you are, you're going to have to wait 360 years or so. Don't miss those. And you should know, it is okay to miss a total lunar eclipse. But you should also know that the moon is around 238,000 miles from Earth, traveling at a speed of 2,300 miles per hour on a month-long orbit around us. And that orbit is not flat, but it's tilted 5 degrees off the plane of the solar system, which means the moon rarely goes into the Earth's shadow. Usually it goes above or below it, except for 1 or 2 times per year on average. And when it does, you can actually see the shadow of the Earth as the moon goes into it. In fact, ancient Greeks have known that the Earth was a sphere for over 6,000 years from observing lunar eclipses. You can't fake a lunar eclipse, flat earthers, I don't think. And when the moon goes into our shadow, it eventually turns blood red. And let's be honest, that's a much better name than a strawberry or a rose moon. Those are terrible ideas. And this happens because the sunlight bends or refracts around the Earth through the atmosphere, scattering all the colors of the rainbow except those with the longest wavelength, red. And this is visible only during a full moon, and only from the night side of Earth. And this time around, only people in the Americas are going to be able to see the full, uninterrupted lunar eclipse. Sorry, rest of the world, if you want a total lunar eclipse from start to finish, you're gonna have to wait, but not long. So should you watch the total lunar eclipse, like thousands and thousands of generations of humans have done? Well, they say there are no stupid questions, but that's one. So go get some coffee and some warm clothes. It's gonna be a long but beautiful night.